in listen-only mode.
Hello and welcome to today's presentation on stormwater treatment systems, sizing stormwater separators and filters. My name is Philip Taylor. I'll be doing the presentation today. I'm a registered engineering associate in New Zealand. I started my career in water and soil conservation. Worked for a few years in the UK in the mid-90s on infrastructure projects before returning to New Zealand, where I spent 12 years working in building products, marketing and sales, and specialised in keystone retaining walls. For the last 11 years I've been working with Hydro International, specialising in stormwater treatment, and recently gained my Certified Professional in Stormwater Quality qualification. I'm going to have a slight change to the presentation. I'm going to talk about stormwater separators more than stormwater filters. The reason being, I started doing this presentation and realized that we had a lot of content to go through within the separators alone. And next week, Jeremy Fink, one of our engineers in our office, is actually doing a separate presentation on industrial stormwater. That's next Thursday, which will cover a lot of filter materials. So rather than double up, I'm going to let him deal with filters next week and invite you to join that webinar. Now, a little bit about Hydro International. We're a company based out of the UK with office locations in two locations in Portland, Maine and Portland, Oregon, basically in the US. We do operations worldwide, work in many countries around the world, and we specialize in stormwater, wastewater and combined sewer treatment systems. Now on this presentation we're going to focus around the Clean Water Act and stormwater separators and what these proprietary systems can do and how we size them and use them. Basically the Clean Water Act 1972 amendments established the National Pollution Discharge Elimination System, and that's what we're all trying to work around at the moment, work within those regulations. What the Clean Water Act did, it required states to adopt water quality standards. It didn't dictate water quality standards, it sort of gave a general guideline of what was wanted out there, and states developed their own water quality standards, and we see a great variety of standards. No one shoe fits all, so we've got a whole bunch of different things we deal with, and not only do we deal with it by a state-by-state basis, it is often a city-by-city or a county-by-county basis, and in some places it's a watershed-by-watershed basis, so we have a real mixed bag to deal with. That makes it difficult to have a solution to a problem like, how do I size my stormwater separator to remove this or that? So there's a lot of questions, and for the technology we have available, basically, when we look at the most common pollutant, which is total suspended solids, and because that is generally used as a proxy for many other pollutants, it's the one we're going to concentrate on. When we look at this, we can get very coarse pollutants, 1 millimeter and above. Those are basically removed by screens or basic settling devices. We move down to the very fine sands, and now we're talking about hydrodynamic separators, more advanced sort of separators. As we go down to the coarse silts, some better designed stormwater separators can do that, but now we're really starting to move beyond coarse silts down into clays, colloidal material. That's where the filters sit. So we're going to look at basically the advanced vortex separators in the range, working within that range of about 20 microns and above. As I say, every state tends to have its own idea of what water quality is. They generally, if we're lucky, will have a water quality event or a water quality volume you have to deal with. Most will define a treatment standard. Usually it's around 80% TSS. It can vary a lot. We can see some regulations written around phosphorus removal. It might be 60% TSS, 50% TSS, it could be X% phosphorus, or it could be an effluent control standard. So we have a lot of different standards we have to try and make this equipment work for, and how to size for it. And when it comes to hydrodynamic separators, there's a lot to choose from out there, and a growing number of different options. So it's not like you don't have options. There are many options. And again, with filters as well, the number of filters coming on the market is increasing as well. So you see lots of different options on filters. Now, really what we want is quality assurance, that if we specify something, it's going to meet the local stormwater standards, and that as an engineer or a reviewer, whatever you use will meet those standards, and that when you do a check, it's a simple check, that you can trust what you're being told. And also it allows competitive bidding, so that if a contractor, inevitably, if a project goes to bid, especially a public bid, one item is specified, 3 items are presented as alternates because A, they can get them cheaper, or B, that's who their supplies. So you need a competitive bidding situation, which is a good thing, but you also need to be able to vet these alternates so that you can have an assurance that if you switch it out for something, you're going to get an equal water quality basis. So these are the things, these are the challenges within our industry. Now, if you are in a state that clearly defines a water quality event, or you're in a city that has a clear water quality event in their stormwater manual, has prescribed a method of sizing a proprietary device, and it relates to the target pollutant, and there's a verification process or a reference you can use, and some cities have this, and you can smile and you can probably give up listening and go off now and do whatever you do. But if you don't, then you really want to listen to the rest of this. Typically, when we look at a separator, just to give you an idea, let's see if this is going to run. Just in case you've never seen inside one of these, this is our Downstream Defender. This is a time-lapse video. It's sped up. Typically, it's showing about a 75 micron particle model here. But the water comes in, these things swirl around. The water separates the sediment from the clean water, basically, and you capture the sediment in the bottom of the unit. And a well-designed device will retain that material. So when the flow increases, as it shows here, the material in the sump doesn't get resuspended and washed out. Now, the newer test standards being used around the country incorporate these washout tests as well. So that's an important feature. So 80% of what is another question as well. Many stormwater standards, or stormwater manuals I should say, often require treatment of stormwater. They say you've got to remove 80% of TSS. Well, what's TSS? It could be 80% of whatever the test protocol asks you to use. It could be 80% of a particle size distribution that was put in the manual that relates to nothing that you've tested with, or it could relate to something that you've tested with if you're lucky. Or is it 80% of what's coming off the site? Now, often the effluent standards are really looking at what's coming off the site and asking for an effluent control. The problem with that is that there's just no way of showing or proving it unless you monitor every site, and that becomes impractical. And also, how do you calculate the 80% removal? There's 2 primary calculations we can do. One is what we call the water quality flow or single event calculation, and it takes a certain event, like it might be a 2-year, 6-month or whatever rainfall, 24-hour rainfall event, a half-inch runoff depth. It's some sort of event that generates a flow that you have to treat to a certain standard. And the other calculation is known as the net annual, or it could be called a continuous runoff model. It's a long-term calculation. It takes historic rainfall data, separates it out into different intensities, calculates flow rates for each intensity, multiplies by the removal efficiency of the device for each of those different flow rates, and sums it all up You end up with a calculation. I'll show you the table in a minute. So if we do the single design storm, we can use something like TR55 HydroCAD. And sorry, this is a little typo there. This is a 4-acre lot, say 90% impervious, typically of a parking lot. And if we wanted to treat the half-inch runoff, and this is something that's reasonably common, it's usually somewhere between half-inch to 1 inch of runoff depth. It's going to generate, and another typo there, sorry, I was altering this, it's going to generate 3.11 CFS of runoff. So that's your peak runoff. So that's your water quality runoff event, and we want to size the equipment for that. And we can go to a couple of sources out there and get some sort of reference. Say, if I want to treat that, I could use the vendor tables. Vendors publish data on various different particle sizes, and you can select that. Or if you want something independent, something third-party verified, I recommend either Washington DOE or the New Jersey Department of Ecology, NJDEP, sorry, Environmental Protection. They have these tables, and they're useful tables, and I can go to this table. This is the Washington DOE table. And say I want to treat that 3.11 CFS, I can go to the table, I can get a Downstream Defender, it's a 6-foot unit, or I can use a Storm Scepter here, 11,000. That's actually a double 12-foot manhole unit. For Technic, 7,000, it's an 8-foot unit. And I can continue through CDS, 8-foot unit, Aquaswirl, a 9-foot unit. So you're thinking, well, quite a lot of variation there in terms of size. So if I was doing this, I might just pick a 6-foot unit because it's the smallest one, cheapest, saves the client some money. Now that's a flow rate sizing. Now if I do the net annual calculation as I described earlier, and I do all these calculations for all these different flow rates on a long-term basis, and I come up with a net annual removal of 87%. If I run that through my little bit of software, because there's no third-party independent software that will do this for you, you've got to use the vendor software. It's going to say I can use a 4-foot unit. Now typically most of the vendor software will end up doing this. The unit you get from a net annual sizing will be a lot smaller than the unit you get from a single event sizing. So, you know, event-based sizing says I can use a 6 or to a double 12-foot unit. Net annual sizing says I can use a 4-foot unit. So what gives here? To understand this, we've got to just look at the rainfall data. Now if I just take this typical chart here, this is from the Minneapolis St. Paul Stormwater Manual. If I do a net annual sizing, I'm calculating sizing based on all these little events down on the bottom of the screen here, and I'm averaging them all up. And so the influence is that the greater number of these smaller storms pulls the sizing down. Whereas if I'm doing a set runoff, a single event, I'm going to size for that single event. And I'm going to treat everything less than that and part of everything above that. So when I look at the test data of why it drags everything down, if I'm pulling my calculation towards smaller flows by averaging out all the little storms and that influence, as you see, when this is test data for multiple 4-foot units using the same particle size gradation, basically OK110, as the flows decrease, their performance converges. So they all tend to converge down to a similar sort of removal. So as you pull the average flow rate down through a net annual calculation, everything converges. And so you'll get very similar sizing, 4, 5, or 6-foot unit. When you size on a single event, you push the flow rate out and say, I'm going to stress that equipment and say I need to treat, say, that half-inch runoff, or whatever it is, and I'm going to come up with a flow rate that's out here somewhere. And you get a divergence where one might be a 4-foot unit, but for another one to get out there, they've got to upsize to a 6 or an 8 to get to that point. So it's kind of a stress test when you use a single event sizing. So that sort of sums up the sizing, the net annual and the single event sizing. Part of this equation is when you need testing and validation, because basically no one can trust the vendors, right? Because they're going to publish the data which really works well for them. But you really want third-party verification and some assurance that what you're putting in the ground, because it's expensive, it's going to be there a long time, and you really do want water quality, right? So you really need to have some sort of validation. So we need validation that allows also new technology. We don't want the validation process to be so onerous that no one gets through it, that you never get new technology. So you need a validation process that allows new equipment to get to the market for a reasonable cost. It's got to verify the performance, and it's got to sort of meet in with your local water quality standards. Now here's where we've got a little bit of a problem in the industry. There's no national validation currently. There is work being done by WEF and a few other standards committees who are trying to get to a national standard. Now that's probably 5 years away. Currently we have two, the New Jersey DEP, which is a TARP standard, technology, I'll go into whatever that is, and the Washington DOE, TAPE standard. So the Washington Department of Ecology uses this TARP, the Technology Assessment Protocol Ecology, protocol to test and verify equipment. Now this is a field test standard. So you actually have to test your equipment in a field installation. Now that is fraught with problems of variability. There's a rule about testing. When you do a test, you only change one variable at a time, so you know when you change something, you know what caused the effect. So you don't go out there and change 3 things and then go, why did something change? What did we change? Because you've got 3 variables. So when you do field testing, everything is changing continuously. The weather, the wind, the deposition rates, the runoff rates, the type of pollutants. So field testing is an extremely difficult thing to do. It's expensive. It's long-term. The weather often doesn't cooperate. So field testing is a problematic test basis. Within the Washington DOE, you get pilot level, conditional use level for and general level. So your pilot level is you submit a bit of lab and a bit of field data, and you get approval to do your field testing because they think it might work. Conditional use allows you to install and sell a few pieces of equipment while you do your field testing, in the anticipation that you'll get the general level designation and you'll be fully approved. Now within Washington, they have the basic general use level designation basic, and that is filtration, because you're required to get at least 80% removal of TSS. And they have a general use level designation for pretreatment for separators. Now, pretreatment is because in Washington they pre-treat their filters with a separator when the influent concentration is to a certain level, so that the filter is protected from extremely dirty water. That pretreatment standard is very high. So if you're doing standalone treatment, that pretreatment standard is pretty good. There are a few problems. When we look at Washington, it was first, I think around 2002, the TARP guidelines were published. It's been updated a couple of times. 2008, it required for pretreatment 80% removal of OK110, which is your coarse sands, fine to coarse sands sort of thing, and 50% removal of fine material, 50 micron. Now that was a pretty good standard. 2011, it was further updated, basically around pretreatment to reach certain effluent limits. So the old TSS limits, as pretreatment, when it came in between 100 and 200 milligrams per litre, It was intended to achieve a goal of 50% removal of fine material and 80% removal of coarse. Now, so you had some assurance that you're getting 80% TSS in there. The current standard, it requires, if the influence coming in from 50 to 100 milligrams per litre, and remember we're protecting a filter downstream, the effluent has to go out at less than or equal to 50 milligrams per litre. So if it's coming in at 50 and it's going out at 50, you can have 0% removal, but technically you've passed the test because it's not going out at 50, greater than 50 milligrams. Let's say it's coming in at 100 and you achieve the reduction to 50 milligrams per litre. So coming in at 100, going out at 50, you've got a 50% TSS reduction. Now, if it's coming in at greater than 100 milligrams per litre, so you're getting some really dirty water coming in, you're required to get 50% TSS. Okay, so if it's coming in at 400 milligrams and it goes out at 200 milligrams, you've got your 50%. So you see, we're now getting away from that 80% TSS requirement. And because it's a field test, this may not stress a piece of equipment. Let's say that you're testing out in Washington where the standard applies and you don't get a lot of very heavy rainfall. You get a lot of long-term small rainfall events. You never stress the equipment to its maximum flow rate, so they allow some supplemental lab testing at the to stress or to maybe put the limits onto the on the device you're testing. And they require the use of a product called Separators 106 as the test sediment. This is really fine material. You can see these particle size distribution charts here. The old OK110, which is about 125 micron, is the blue line. That had a particle size of around D50, around 110 microns. So it took about, it would settle around about 6.1 millimeters per second, reasonably quickly. The new Separators 106 has a D50 of 24 microns. Now that's beyond what we can remove basically with separators. And it settles about 20 times slower than the OK110. So to get 50% removal of that with a separator means removing basically everything over 20 microns, 24 microns. And that's a big ask. So this list that we see with Washington now is a small list. It's actually only about three vendors in there because Contech own about 3 of these products. And since this new standard has come in, only one vendor has added to this list. Now, the problem with the pre-treatment part of this is that if I wanted to do this test so I could sell my separator, I have to have a filter that I can sell with it, because those vendors out there with both a separator and a filter will package them together and sell them as a treatment system, and they won't allow those to be separated. So we can't just sell or go through this test and spend all this money just for a separator because I'll be packaged out of the market. So this list is limited to the vendors that can provide both filters and separators, which means that if a new separator comes on the market, it's never going to go through this test by itself. The vendor will just call it and say that's not worth doing. So we have a very limited list here. And the other problem with this list is it has some legacy in it. When it comes to testing, you test a 4-foot unit, and what you do is you scale up using a scaling equation to your 6, 8, and 10s. Now the simplest way of doing that is a surface loading rate, constant surface loading rate, just like you design a pond or a settling basin. So if I use constant surface loading rate and I scale, say, my 4-foot downstream Defender, which is the product we have, and go to a 6, and let's say I get approved for 1 CFS and I scale up to 6, I get 1.25. However, because in the early stages of this industry, we allowed volumetric test scaling, where we took the vertical component as well as the surface area. When you use volumetric scaling, you go from a factor of 2 to something greater than 2. So I can scale from a 4 foot to a 6 foot. Instead of going from 1 to 2.25, I go from 1 to 3.2. Now, that has a big influence. When I look at the approvals currently within the Washington DOE, I take my 4 foot unit and go to a 10 foot unit under volumetric scaling because it's a legacy device. I can treat up to 17.1 CFS in my 10 foot unit. Where a current device is limited to surface area scaling, they can take their 4 foot unit and scale it up to a 10 foot and actually be at 4.03. So there's a significant influence on the scaling. So we have some inequity in this chart. So really, when we look at Washington DOE as an option, it's a small list of vendors, it's expensive and time consuming to get through, and it has some legacy problems in it. And it's not really going to be favorable to new technology or new companies coming along because there's a huge barrier to entry and cost and time here. So what options have I got? Well, New Jersey is an option. The TARP protocol, the Technology Acceptance Reciprocal Partnership, TARP. Now, everything that Washington DOE is now, TARP used to have those same problems. Now, so they had the scaling problems, they had all sorts of problems, and I'll go and just explain a couple of those. But back before 2015, they had all sorts of problems. It was all based on 2 stages, basically a lab test stage followed by field verification. So you could get to a certain level of certification through lab testing, which allowed new technology to get a start, and then you could start working on your field verification. No matter what you did, you got approved for 50% TSS. So even if you removed 80, for a separator you got approved for 50. If it was a filter, you got approved for 80%. So initially, when it first started, vendors submitted data that they had already test data for that was close enough to the protocols, in the hope that they wouldn't have to redo all the testing and go through the cost. They submitted data that said, look, can you look at this? If it's good enough, can you use it? And in some cases, it was accepted. Now, within that process, you state what your treatment flow rate will be. That will be the stated treatment flow rate. That's your 100% flow rate. And then you tested various fractions of that, 25%, 50, 75, and 125. You get your removal efficiency for those different flow rates. You multiply by a local New Jersey weighting factor to get a weighted removal efficiency for each flow rate, and then you add it up, and you've got to get over 50% to win. Okay. So vendors did this, and they realized, okay, we can submit the data. We got 80%. We get 70%. We get certified for 50. Well, later vendors realized this and think, hang on a second. If we only have to get 50%, why am I submitting data for 80%? Really what I want to do is state my 100% flow rate and do some pre-testing and try and get as close to 50% as possible to maximize my flow rate to have a commercial advantage, that I can put more water through so when I scale up, maybe I'll have a smaller device than my competitor. So you started to get all this imbalance within the New Jersey standard. And also there was some craziness going on with scaling. So New Jersey Reset, they just said, that's it, we've had enough. There's a lot of infighting going on here. There's some valid concerns. So they wiped the board clean. They got out the eraser and just wiped everyone off and said, that's it, start again. 2015, you have to resubmit data. It's all going to be lab-based. It's all going to be based on a common protocol. It's all going to be common scaling, and it's all going to be done the way we want it done. And you're going to get certified 50% TSS for your separators and 80% TSS for your filters. Okay, See the problem here? Many stormwater manuals are asking for 80% TSS. Okay, so how do we get a solution now? Now we've got two verifications we can look at, Washington DOE or NJDEP. These are the closest things we've got to national standards. In fact, the New Jersey standard has been recognized internationally as a clearinghouse. So it's used in Canada, it's used in Australia, it's used in other parts of the world as well, Malaysia. They reference it. So it's becoming quite a standard. The test sediment used within Washington, used within New Jersey, is a blend that they've come up with a D50 around 70 microns. Now that's a little more friendly to separators, and it's a little more practical when you start testing separators. So if we compare the old OK110, which a lot of, we have a lot of legacy testing on, and in fact it's used still as a standard by many local stormwater agencies. This is the New Jersey one, the green line in the middle, with a D50 around that 63 to 75 micron. And here's the Circle Cell 106 used by Washington DOE, which is around 24 microns, way beyond really what a separator can do. So here's the crux of it. We look at the test table, comes out, we have our stated flow rate. In this case, we've got a stated flow rate or a target flow rate of 1.13 CFS. We do the testing at various fractions of that. And we measure a removal efficiency. And notice here, none of these removal efficiencies in this column in the middle are over about 60%, because you didn't have to be. You multiply your weighting factor, you add it all up, just over 50%, that's what you need, you get approval. So what if you want that 80%? This is a conundrum. We solved that problem ourselves within hydros, because what we did, when we did our testing, we didn't measure the mass of everything as a total. We actually measured individual particle size ranges going through the device. So we separated out the New Jersey particle size gradation into its little constituent parts and measured what was going in and coming out for each particle size. Now this gave us a really interesting insight into the performance of separators, because now we can look at 1000 micron, 500, 250, 150, etc., right down to 2 micron, and see what was going on in terms of a percent removal. And what we found with our first defense unit, typically down to 50 micron, you're getting positive removal, and once you drop down closer to 20 micron, basically you're getting no removal. It's showing negative removal, but when we look at the actual numbers, 22.4 in, 22.6 out. So basically within the margin of error, everything that was coming in was going out. And at 20 micron, you expect that with the separator, because they're not designed on typical sizing to remove these very, very fine particles. And so when we look at these numbers, also the closeness of the numbers gave us assurance that we knew what we were putting in, because we had the dry weight of the material, and our sampling on the outside, on the back end, where we were doing the effluent sampling, was very close. So we're getting some fairly accurate numbers here. So down to about 50 micron, we're getting pretty good removal. The downstream defender, when we retested that, we did the exact same thing and got the same answer. Down to about 50 micron, we're getting good positive removal, but down to 20 micron, again, everything that's coming in is going out. So if we just looked at the particle size distribution from 1000 micron down to 50 micron, which is coincidentally has a D50 around about 121 micron, whereas the OK110 had a D50 around 110 micron, which is pretty close, we get about 83% removal. So there's your 80% removal. So we can translate or infer that if we do the New Jersey testing using the New Jersey particle size distribution, and we get approved for 50% TSS at these flow rates, we're most likely to be getting 80% TSS on an OK110 or similar, say 120 microns, 125, 115, around that range, which is a good water quality standard for a separator. So I can do a calculation for my water quality event using the local stormwater manual and come up with a flow rate. I can then reference that flow rate against New Jersey, ignore the fact that it says 50 and just say, well, that's 50% of something that's very fine. It's more likely to be close to 80% of, excuse me, of a coarser material, which is more likely what I want for my separator, and just use these numbers, knowing that all these numbers are based on the same test protocols, the same particle size distribution, and the same scaling equation, all verified through the New Jersey Corporation of Advanced Technology and then certified by NJDEP. So this becomes a very solid list to use. Now, one of the big advantages of this list is it's growing, because being a lab test process, it has a much lower barrier to entry. So if I come along and I have a brilliant idea and I've got a new piece of equipment, it's the best thing since sliced bread, I can put it through this and I can get a market in Canada, I can get a market down the east coast of the US and throughout the US in fact, and overseas, making it practical for me to do this and giving engineers access to a new technology. And if someone wants to propose an alternate, you can just say the alternate has to come from that list, and you can do a direct flow comparison saying, well, the alternate for, say, a 6-foot downstream defender running at 2.52 CFS, you would need a CDS 7 or maybe an Aquaswirl 7. So it gives you some equity, and the sizing's a little closer because of that, because they've got equitable scaling. So there are some advantages now to the New Jersey list when it comes to sizing separators over the Washington DOE. And when I compare those flow rates to, say, there's the city of Indianapolis has an excellent table that they've put together for 80% removal of OK110, and they list a range of products and they assign a flow rate to those products. It's similar to the New Jersey list. So it gives some validation or verification that the two lists aren't too far out if you're looking for 80% removal. All right, that about sums it up. It's a lot to go through, and that's the reason I didn't want to go into filters in great detail, and I want to let Jeremy talk about that next week. We've already gone through about 40 minutes of presentation. I'm sure you're getting tired of listening to me. Now, if you have any questions, please feel free to email them. My email address is right there. It's ptaylor@hydro-int.com. Follow me on LinkedIn. If you have any questions, just email me or I'll answer them directly. If you need a PDH, we're going to send out a follow-up email with my details, and I think we're going to send out certificates for all attendees as well, so you'll get PDH certificates as well. This is recorded. We'll put a link up to this recording as well, so you can follow up or send this on to other people to listen to. And with that, I'd like to thank you very much, and I hope you have a good afternoon.